So this one is totally virtual. We go to this place that we do lab before. So in this one, you don't need to download it. You can just run it directly. This is called collision lab. Now, so what do we do here? So we're gonna talk about basically some collisions, and we're gonna try to use conservation momentum. We'll testify conservation momentum here, okay? I got another message. Let me take a look. Oh, that's again about homework. So we'll talk about that later. So, so basically you have a lot of trials here, but they're all virtual. So it's pretty simple. So what I want to do is like explore these collisions that we talk about in class, like elastic and inelastic, so that you can, so basically you see, as you see here, right? There are two balls here and you have given mass here, okay? You can change the mass you want by moving this like that, you know? And you can also, yeah, you can try to choose to show, see there's an elastic one and inelastic one. So we're gonna do 100% elastic or 100% or like inelastic, which is these two extremes, okay? So basically what do you do here is, so that you can change the speed as well. Hold on, no, this is not the speed. So this is the speed vector. I think that's like a given. So, okay, the velocity, yeah, you can change the velocity from here, okay? So normally what we do here is we keep one ball at rest, the other ball moving with initial velocity, and then we let them collide. And then after collision, you'll see different kind of phenomena, behavior of these two balls, depending on their mass and depending on whether they're elastic or inelastic. So there are basically four different parts of things you do. Each part you do like 3 trials. The first one is a elastic collision. Okay, give ball 1 non-zero initial velocity, ball 2 0 initial velocity, and then consider these 3 cases. Equal mass and ball 1 is smaller mass than ball 2, ball 1 has larger mass than ball 2. And you see that their behavior is totally different, okay? So restart. So let's say, I'm gonna show you a little bit and then try to explain. So let's say, suppose you have like say equal mass, okay? Both of them have 1.05, wait, let's say like that, okay? Now, when you let it go, elastic collision, see, what happens after collision, ball 2 goes with the same velocity as the initial velocity ball 1. Like again, initial velocity ball 1 is 1. See, after that, they just exchange velocities. Very interesting, right? Now, however, if you have the mass of ball 1 is smaller than mass of ball 2, things are going to be very different, okay? See, ball 1 start go back, ball 2 go forward, okay? Now, remember we discussed this in our lecture, and we have some formulas here, and you don't need to use the formulas, but you can check if you're interested. These are the formulas, and they all agree with the formulas. In that case, remember we have V1 prime equals to 2 M1 minus M2 divided by M1 plus M2. V1, and then V2 prime equal to 2M1 divided by M1 plus M2 V2, okay? So these two formulas are the formula you can predict these two final velocities given the equations of conservation momentum, conservation energy. You don't need to know this, I mean, to do the lab, but it's kind of interesting to check. Actually, they actually work, okay? So these are the first 3 trials, and then the second 3 trials is you do the same for the total inelastic collision. And remember, when you have total inelastic collision, the 2 balls actually stick to each other. So if you do the same for like equal mass case, okay? See, after collision, they just stick together, go forward. They don't bounce back anymore because this is total inelastic, okay? If you change your mass here, again, similar things happen, they also stick. So in the case of total inelastic collision, it's kind of you got very similar result, but the numbers of the final velocity is going to be different. For example, in this case, right, start from 1, you got 0.05, 0.25, okay? Well, if you have equal mass here, see, you got 0.5. So the velocity numbers are going to be different, okay? So that's the second 3 trials. And then the third 3 trials here, now I want you to do like for both of them has velocities, but opposite direction. So, and then again, you will see some interesting phenomena here. For elastic collision, for example, I'll just give you some like equal mass. Okay, like say this one has negative V1. So they kind of go together. It's like a head-on collision, right? Okay, so interestingly, after collision, they stop, okay? Because they have exactly equal amount of momentum, but going to the opposite direction. So they stop here, okay? And so the momentum is still conserved, okay? But again, if you have different mass here, for example, ball 2 has larger mass, now it's gonna be different, you know? See, they're gonna go one direction because this one has bigger momentum than that one. So again, it's kind of interesting to see that, you know, it's different from the case when one of them going to the other, you know? And for total inelastic, same thing. Okay? You have some different results. But in this case, actually, you'll see that there's it's very kind of similar to the elastic clearance. So for example, let's say oh, I'm sorry. Yeah, I was talking about inelastic clearance. So let's go back to elastic. Let me show you the elastic again. So let's say equal mass. I think elastic is like, they don't stick to each other. Elastic, they collide, they bounce back, okay? Well, when they bounce back, they again exchange velocities, okay? Yeah, I'm sorry that I made a mistake in talking about that previous case. So when it's totally elastic, okay, you have equal mass and different opposite direction of velocity and equal magnitude. What's happening after collisions, they bounce back? Well, why don't they stop there? Because if they stop there, the energy is not conserved anymore. So you start from kinetic energy and then you end up with zero. That's not right. So they would exchange velocities. Ball 1 got a velocity, ball 2 got a velocity, ball 1. So, and this is totally different from the inelastic case when you collide and then stop there. So in that case, wait, why don't they got it? No, oh, I see. It's not totally. I need to put a total inelastic. Okay. So in that case, they stop here, and because energy is not conserved, so all the energy is lost in this case, okay? And momentum is conserved, and all the energy is lost because they need to stick together. So again, you will see something very different when you have elastic collision when they do not stick to each other, but have different. Let's say when you have different mass, again, it'd be kind of interesting. Well, it depends on the mass ratio and everything, but you have different phenomena. So anyway. So that's basically those 6 trials. Now, what you do here is when you do things, you actually have the mass given, right? You set them up. Sometimes they're equal, sometimes not equal. And then you put them, when you change the mass, you can change only one of them, leave the other one the same. And then you get the initial velocities set up, and you get the final velocity given as well. So you have all of these, and then you can go ahead and calculate the momentum. Well, they give you the momentum here, but I want you to calculate them by yourself and show your calculation here somewhere on one of the pages, and then calculate percent difference. And certainly because it's a virtual lab, you're going to get perfect results. So the momentums are going to be totally conserved. But again, the point for this virtual labs for you to see the different case of collisions, like elastic versus inelastic, and you can get different answers. Okay. That's all I want to talk about for the second one. Okay. Any questions about the second lab?